Again, in special relativity, where we have so-called flat space-time, we have a space-time interval between two events which are infinitesimally close to each other in both space and in space and in time. Note in the definition we have a negative sign here. If you calculate this integral between event number one, so that means specifying time and position for event number one, and for event number two as well, if you calculate the integral of the square root of negative ds squared, the trajectory a particle will naturally want to move along will be one that maximizes this integral. Negative sign here, it looks like we're taking the square root of something negative. We're not. Because objects cannot move faster than the speed of light, it turns out that if ds squared is a space-time interval for two events along the trajectory of one particle, of one object, it turns out that this ds squared will be a negative quantity. So negative ds squared will be a positive quantity, okay? So why is that true? Again, you can work it out for yourself looking at equation 4.26. If you insist that objects do not go faster than the speed of light, ds squared is negative, so negative ds squared is positive. Okay, so you'll go through a problem in your last problem assignment where you investigate this a little bit, well, in some detail. Okay, now all of this corresponds to the special case of special relativity. Special relativity is one where we have flat space-time, where the space-time interval equation looks like this, equation 4.26. Now it turns out that in the presence of gravity, gravity will distort space-time so that equation 4.26 is no longer true. There's something in general relativity called the Einstein equation, which will provide the correct form of ds squared. So if you're near a black hole or a neutron star or some massive object, it will change this equation into something more complicated as a result of the fact that matter and energy will bend space-time, so it is no longer flat. But the interesting thing is, particles will still move along trajectories that maximize this this integral. Okay, and this is all of this is, as I say, in the context of general relativity. So if you're curious about this, you can take my general relativity course, which is offered not next year, but the year after next. Okay, so let's leave that aside for the moment. Let's come back to the brachistochrone problem. Okay, so remember what the brachistochrone problem is. The brachistochrone problem, sorry, let me just find the figure. It was this one, right? Okay, so here's the brachistochrone problem down here. Okay, you have a track which is frictionless. An object starts from rest at this point. It slides down along this track. You want to determine the shape of the track, which is given by the function y is equal to f of x, that will minimize the time it takes to go from the first point to the second point. And remember, what we determined was the time it's going to take, as long as the track is frictionless, time is going to take is given by this integral. Okay, so we have an integral here. Now we have a constant out front. We don't really care about the constant. Okay, because we want to minimize the total time, we need to minimize this integral. Okay, so with reference to equation 4.6, that was the equation which provided the general statement of the problem. So look back at equation 4.6 in your notes. You can immediately identify big F as simply the integrand in this integral. It does depend explicitly on y. Here's y. It does depend explicitly on y primed. In this case, as in the other case that we looked at, there is no explicit dependence on x. Okay, so it only depends on y and y primed in this special case. Okay, so we're going to apply this to the Euler equation. So the sensible thing would be then to take the two partial derivatives, df by dy, df by dy primed. Here's what big F is, so you can take the derivatives. Here's the first derivative with respect to y. Here's the second one with respect to y primed. It's getting kind of complicated here. And then if we substitute both of these into, oh, wait a minute, no, we have to do one more thing. Before we do the substitution, we have to take the derivative of this derivative in equation 31 with respect to x. And we're going to have to use the product rule. Well, there's y primed, and here's another factor of y primed in this third factor, or occurrence of y primed in this third factor. Okay, things are starting to get very messy here. So when you substitute into the Euler equation, it gets very messy. We get a very messy differential equation. And we don't actually want to do that. There's a better way to solve the problem. Okay, what we're going to do, so this is a little trick that will simplify this problem. And this problem is not a simple problem, but it's even with the alternative approach we're going to take, but it's much easier than would be the case where we try to solve this messy Euler equation, which results from substitution of equation 32 and equation 30 into the Euler equation. So the idea is basically we're going to swap the roles of x and y, and you'll see why this is a useful thing to do shortly. Okay, first of all, we note that dx is just dx by dy multiplied by dy. We can call the first factor x primed, where x prime just means dx by dy. And remember that y primed is dy by dx, of course. Well, that's the reciprocal of dx by dy, as long as that's not equal to 0. As long as dx by dy is not equal to 0, we're okay. Okay, and we're going to assume that that's the case. So this derivative is the reciprocal of the other, assuming this is not 0. But dx by dy is, we just said, x primed, so y primed is therefore 1 divided by x primed. Okay, so if we go back to this integral, here again is the integral. We replace y primed with 1 over x primed. We replace dx with x primed dy. Okay, and we have an alternative form of the integral which emerges. Okay, so you'll notice what I'm doing here. I'm multiplying x primed into the square root. So I take the square of it and the square root, and then I bring it into the square root, and it simplifies into the expression that you see in equation 35. You can do that math yourself. That's not difficult. Okay, so now what we have is a case where we have an integral which is a function of y. It's a function of x primed. Most generally, you might sometimes find it to be a function of x as well. We do not see that here. Okay, and the derivative, the integral, is an integration with respect to y. So y is now the independent variable. X we're now treating as the dependent variable. Okay, so this looks just like the original statement of the problem from a few slides back, with just the role of x and y interchanged. And this big F is clearly just whatever this integrand is. The integrand is square root of x prime squared plus 1 divided by the square root of y. Okay, now we can use the Euler equation. Now I've made a couple small changes to the Euler equation. The roles of x and y are interchanged. So where we had a df by dy, well, now we have a df by dx because x is the dependent variable. X is now a function of y. That's the function we're looking for. And we have df by dx primed, partial derivative here, and then we take the derivative of that with respect to the independent variable y. Okay, what do we do now? Look at equation 37. There's big F. Do you see an x anywhere? No, only x primed. So df by dx is equal to 0. Oh, okay, this looks like a useful thing. It's starting to simplify. So that means that, let's see, df by dx primed is going to be a constant. Okay, why is that? Well, look at equation 38. This term is equal to 0. It means the derivative with respect to y of that partial derivative, df by dx primed, is equal to 0, again, because that second term is 0. Well, if the derivative of something is equal to 0, it must mean that something, which is this derivative, df by dx primed, it must mean that it is constant with respect to y, the dependent variable, y, independent variable. Remember, y is our new independent variable. Okay, now df by dx primed, if you calculate it, we know what big F is, calculate df by dx primed, you can do that derivative of equation 4.37. When you calculate that derivative, this is what you get, and it is equal to a constant. We've just argued equation 440, it's equal to a constant. Call that constant the square root of c. Why are we putting a square root around it? Well, don't worry about that yet. Call this constant, call it the square root of c. Now, maybe you'll see now why it was a good thing to call that the square root of c, because we're going to square both sides, and after that we're going to solve for x primed. You can do that math yourself. Square the left side, square the right side, square roots will go away. Rearrange the equation, okay, and then solve for x primed. This is what you get. And what is x primed? Well, remember, well, here's the value. Here's what you get when you solve for it. But remember, x prime was defined as dx by dy. So now we have a differential equation. Here is our differential equation. Dx by dy is equal to some function of y. So all we have to do now is solve this differential equation. Then we will have x as a function of y. That's the same thing as having y as a function of x. And then we will have solved the problem. Okay? Okay, now the problem with this, proceeding after this is actually kind of a tricky differential equation to solve. And you won't be able to solve it unless I tell you what the trick is. So the trick is we're going to introduce a new variable, call it theta, and we're going to define theta such that this constant c times y is equal to sine squared theta over 2. Okay, from a trig identity, that's the same thing as a half times 1 minus cos theta. So clearly dy, if you divide each side by c, then take the differential, dy will be 1 over 2c times sine theta d theta, right? Just from the right-hand side of equation 44. The other thing to note is dx is just dx dy multiplied by dy. Dx dy, well, let's see. C times y is equal to sine squared theta over 2. Substitute that into these two places, top and bottom, in equation 43. Okay. That gets multiplied by dy. Here's the expression for dy. This reduces to what you see in equation 47.